All right. Well, it's 10 a.m., so I'd say it's time to kick this off. Thanks to everybody for being here in person and online for our first BEG seminar of the year. So just a quick couple of housekeeping items. So my name is Justin Thompson, and I, together with Andras Fall, we are the hosts for this year's BEG seminar series. Presumably you're here, so you know this already, but just to be clear, we are doing a different day, time, and location for the seminar series this year, as well as different calendar invites. So we're doing it Tuesday mornings, 10 a.m. And in-person option is here in the VR room. An additional note, we're doing the calendar invites differently, right? So everybody hopefully got a single multi-event calendar invite a couple weeks or so ago. You need to accept that calendar invite, and it's got placeholders that will be updated with the information for the speakers as we roll along. That email went out to JSG seminars, which my understanding is also goes to BEG, all staff and whatnot. But if anybody has any problems with any of that, let Andras and I or perhaps Jennifer know. Okay, so that's quick housekeeping. So it's my pleasure this morning to introduce Robin Dommisse, excuse me, I did it again, to be our first speaker. Robin he started building 3D geocellular models at UT-BEG 35 years ago. Let that sink in for a moment. Prior to spending 25 years in the oil and gas industry. So that is a wealth of experience. He used his background in geology and reservoir engineering to create 3D models for some of the largest oil and gas reservoirs in the world, including the Ghawar field in Saudi Arabia and 8 major shale and tight oil basins in the US. And today he's going to talk to us about paradise lithofacies and fault prediction, machine and deep learning applications in the Permian Basin. So with that, I will hand it over to Robin.
Thanks, Justin. So this is the first part of my talk will be about Paradise's ability to generate the self-organized maps and now introduce a new capability that just came out here in the last month, which focuses on applying machine learning for lithofacies prediction. The other technology Paradise has is the fault extraction, and later in this presentation we'll show you how we applied that to several of our 3D seismic volumes in the Permian Basin, most notably the Southern Delaware Basin. So for machine learning, we need lots and lots of data. We had a recent seminar here at the BEG where we talked about some of the requirements and needs for machine learning. So several years ago at RCRL, in collaboration with TextNet, we started building what we refer to as the Permian Super Basin model, integrating as much of the stratigraphy and the data that we have available at the Bureau, which of course has been studying the Permian Basin for over 100 years. So the view that you're looking at right here is the Delaware Basin together with the Midland Basin, Central Basin platform in the middle, and some of our beautiful honored West Texas Geological Society cross sections, which we have geo-referenced. So our RCRL focuses on doing both regional as well as field-based reservoir characterization studies in the Permian Basin. So you see lots of examples here from Baskin to fields that we collaborate with Oxy, such as Salt Creek, Johnson. We've built regional models for the Wolfcamp studies, integrating some of the work of the RCRL PhD students. So we've been focusing on the Permian Basin over the last couple of years, both regionally as well as in detailed field studies. So the workflow we use for that is a wide range of software. So software plays a very important role for us to be able to build the proper research foundation upon which to layer our next generation research. So the most exciting new software products that have come out most recently are, of course, we're big Petrel users at RCRL, so we've been using that for quite a while. A big influence came from our friends at the Elise PaleoScan software, and I've given several presentations of that. Just 2 weeks ago, I had the opportunity to present at their users group meeting. So I've got a good relationship with these guys, and it's been a lot of fun being able to discover this late in my career, brand new software that can actually really make a significant change in efficiency and speed. And that doesn't happen too often in one's career, as you can imagine. But especially because in our particular Permian Basin laboratory, looking at all these different data types, we deal with vast numbers of data and a very limited number of time. What's been very exciting, and what you'll see in this presentation, is that they recently discovered a new piece of software that will help my efficiency and productivity, and that's called Geophysical Insights Paradise software. So the studies for the Permian Basin model, of course, have to be rooted in Charlie Cairns' 30 years worth of work in the West Texas outcrops. So this is his conceptual model that guides all of our subsurface interpretations based upon seismic and well-log data. So this is based upon the work of dozens of his students over the last 30 years, and is an important part of the foundation of our research. So to build this giant model, we have collected about 360,000 Permian Basin wells that contain any sort of stratigraphic information. We have access in our collaboration with TextNet to about 75,000 wells that are of petrophysical well quality, so a minimum of a triple combo or a quad combo. What you see right here is a picture of all of the highest quality quad combo LAS wells that we have available in the Permian Basin. So looking from left, we see the Delaware Basin, the Central Basin Platform, and the Midland Basin. And then we've collected, based upon untold number of studies, as well as our own work, and most notably the work of people like Buddy Price, who's now at Devon, who was one of RCRL's and Charlie Cairns' students, who did a lot of very important shelf to slope to basin well log correlations on literally tens upon 10,000s of wells. All of that data is integrated, and we built multiple versions of this 3D model. This is approximately 3.2 million pics that we have collected. And the reason for why we build multiple models is because we want to have a model that is compatible with what the industry thinks stratigraphy is, but also based upon what we think is our next generation best quality stratigraphy. So we'll talk a little bit later about how valuable Paradise has been in the integration of this petrophysical and stratigraphic data, in combination, of course, with the seismic data. And we're very lucky at the Bureau, especially working with RCRL and TextNet, to have collected approximately 37, now 38 3D seismic volumes. And this picture shows all of these volumes from the southwest of the Permian Basin distributed throughout. So the stratigraphic interpretations based upon our well-log interpretations and our seismic data, which of course validates as well as adds to the stratigraphy, has led last year to one of the first versions of the Permian Basin model, which was based upon 37 Permian Basin-wide horizons, which are shown by this fence diagram. And of course, once we build a three-dimensional model, we can build stratigraphically from the bottom up, showing the actual thickness layering of the buildup of the Permian Basin. So this model right here is approximately 2.4 billion cells. And what you need for that is a fairly reasonable computer. Mine has approximately 32 CPUs, about 256 gigs of RAM, and is a fairly new machine capable of handling this size model. So that was last year's model with about 37 horizons. Since then, we have worked on our next model, which contains 100 formations throughout the Permian Basin. And this is one of the results of that. What you're looking at right here is a picture from the southeastern corner to the looking northwest across the Permian Basin, showing a distribution of sonic log derived velocities, a very important product that we need to get in 3D for the TextNet group for the purpose of earthquake seismicity relocation, as well as time depth conversion of all of those seismic volumes. And that's the zonation for the Permian super basin model. And this model too has about 2.4 billion cells. So now we'll talk about the study that Charlie and I did on the Midland Farm unit, in focusing on the San Andreas Grayburg, using the acoustic impedance inversion work in combination with Charlie's core description, in order to try to build a geostatistically based acoustic impedance inversion derived facies distribution, or to create a 3D lithofacies architecture. So the location that you see right here, I'll try to point it here with my mouse. I can do one of these cute laser pointers right there. So that is the location of the Fasken Ranch 3D seismic data set, which sits right on the shelf, the slope, the basin edge of the eastern flank of the Central Basin platform, and a great study laboratory to apply all of Charlie's hypotheses and interpretation techniques. So Charlie interpreted 17 new cores, and it was our job to try to integrate his core facies description with the highest possible resolution stratigraphic framework. So this is the particular workflow. We start off with standardly with layering, with modeling, incorporating well logs, building geomorphologically sliced three-dimensional seismic volumes, and ultimately do a lot of work integrating the acoustic impedance inversions in order to be able to come up with the actual three-dimensional model that tries to highlight these ooid grainstone distributions throughout this field. So a lot of work that goes into it. Some of it takes months, some of it takes weeks, but this is the particular workflow that kind of describes how you ultimately build one of those three-dimensional geological models that can actually discretize these very important flow units in the field. So we started off with a bit of a regional approach. We used the PaleoScan software in order to be able to build a geomorphological framework, a chronostratigraphic correlation framework that was able to properly capture the prograding ooid grainstones in the field. And if I hit the space button right here, then you can see what it looks like in 2 dimensions. On the right-hand side, we have the bird's eye view. We see the acoustic impedance slice using the geomorphological chronostratigraphically equivalent layer. You see that the purple layer right here, see if I can point at it with my mouse, is moving upward, and you see how it's capturing all of the prograding grainstones, showing this infill in the Midland Basin from the north. So, now, since we're talking about software today, I'll make this point again and again about Paradise, but this is another little shout out to PaleoScan. This would have taken me half a year to do in Petrel, manually correlating each and every one of these ooid grainstone structures. With the PaleoScan software, I was able to do that a lot faster, and I've done this in previous talks. So the idea is, though, it's very important. That's the reason why we work with Paradise, is to basically leverage software that can do the work faster in order to rapidly accelerate our research, in order to create products such as this, where we can capture the entire Grayburg, San Andreas infill in the Midland Basin from north to south, showing the actual channel incised clinothems in the Grayburg, right, and showing the actual transgression and regression in throughout the depositional history of this part of the Midland Basin. So all that stuff, lots of work, very important. Got to keep plugging away at the software to make all this stuff happen, and it's pretty time consuming. So here's some more examples of those channels in the Grayburg Clinothem, and this is Charlie's conceptual geological model referencing the actual depositional environment analogs in northwestern Australia. So our job is to now start focusing on the detailed parts of this Fasken Ranch, specifically Midland Farms, in order to discretize, capture, and quantify these very important flow units that are characterized by both the some of these tight and as well as porous grainstones, and the actual structure and the geomorphology of these prograding ooid grainstone successions. So that's where the core data came in, and what was very important for us to be able to immediately establish a link between the core data as well as very high resolution stratigraphic framework. So what you see at the top is the core data. That's just a couple of feet thick. You can see at the bottom, based upon those black lines, that we've been able to get the resolution of these layers for our geomodels down to just a handful of feet, approaching both of the well log resolution as well as the core data resolution. So then, of course, important part about using stratigraphic interpretation tools that are based upon geological concepts. In the past, over the last 30 years, I review a lot of three-dimensional modeling results, and you see a typical top, you see a base, and then people start building for a particular formation, such as the Grayburg or the San Andreas, layers parallel to the top and the base, proportional layering, And that's shown right here by the red zones. Now, if you compare the red zones against the backdrop acoustic impedance inversion product, right, you can see that the match is not very good. Using the PaleoScan software, we were able to put in 300 individually tracked, high-graded, and interpreted horizons that would then capture the actual lateral stratigraphy of the oil reservoir much, much more accurately. And this is very important because that controls how you distribute your actual petrophysical attributes. And that in turn is absolutely critical for affecting your machine learning results. Right? One of the things that I almost completely skipped over here because of the time constraints that we have is how much time is spent on time depth conversion based upon velocity modeling. We spent a lot of time on that because if you can't get your depth petrophysics in proper alignment with your time seismic, your machine learning results will show some very, very interesting mismatches. Right? So the actual geomodeling layering systems also have an important influence on the quality of your machine learning results. Then we, of course, incorporate all that stuff. We show the layering of the acoustic impedance inversion together with our core data, because it's all about trying to validate the distribution of our acoustic impedance derived lithofacies models. So this shows Charlie's interpretation, and then it was my job, based upon his core, then it was my job to basically capture that using a geostatistical acoustic impedance inversion linked distribution of actual facies in order to come up with the best possible lithofacies model in a quantitative geomodel that would match his conceptual geological model.
This video shows the geostatistically distributed ooid grainstone facies thickness accumulation from the base of the reservoir upwards, giving insight into the overall connectivity and continuity of the reservoir flow units.
But here, what we see then is that we get to the quantification of these ooid grainstone clinoform structures, where we show the actual acoustic impedance distributed. We know what the isolated volume is for connectivity and continuity analysis. We can do actual measurements on it, how thick is it, how long it is, how wide is it. We can then look at the actual distribution of the cell thickness throughout the model. We can get the top of it, right, to communicate with other applications, the actual thickness of the grainstone body. We can start cutting through the geocellular model, looking at the actual geostatistically distributed acoustic impedance based realizations. We figured, okay, that's a good test for us to see if the Paradise machine learning lithology prediction can actually be applied to try to replicate the workflow that we did in the Midland Farms unit in approximately 3 weeks. So that was my time in order to be able to build that model to get to the quantification of the ooid grainstones that you saw in the previous image. So I said, okay, I'm going to take a day. I'm going to take a full day, and I'm going to watch all of the webinars that Geophysical Insights has available on YouTube as well as their support website. And I learned in that day from Alvaro Chavez, who is one of the geophysical advisors, as well as Rocky Roden, who those of you that have been in this industry, you may have heard of his name for many years. Thomas Chaparro is the product manager, and those three voices basically guided me through an excellent webinar that explained how to do lithofacies prediction using machine learning. Apart from those people, of course, associated with Geophysical Insights, I should have just listened to the current AEPG president, Deborah Sackery, and there's a list of some of her excellent YouTube presentations, webinars, as well as industry publications, because I probably would have been convinced already. So I highly recommend you tracking down all of her insights into the applications of the Paradise machine learning software. So these are the claims. A statistically reliable description of the subsurface. Well, that's what we're all looking for, right? The time and the cost and the effort, something that we, even in academia, are very, very familiar with, is significant. So when somebody claims that they can do the same type of typical impedance inversion-based reservoir characterization work in a fraction of the time, of course, when I saw that claim, I was very intrigued, right? The interpretability of these results are then compared directly to previous studies. And that's why we picked the Midland Farms unit project, we wanted to compare the results of what Paradise could do directly with a study that we've done before, in order to see if there is a comparable results in the reservoir characterization. So these are bold claims from Paradise. So I took one day, started building my first self-organized maps. This is just a quick slide to explain to you, and most of you people in the room know this stuff better than I do, but I just wanted to make sure that we kind of define what self-organized maps are, how the clustering takes place, and how some of these clusters, which Paradise calls neurons, are then integrated with the actual lithology derived from the well logs in order to come up with a three-dimensional distribution of lithofacies, right? So these self-organized maps, absolutely critical. We do a principal component analysis on the 3D seismic attributes, a very slick workflow in Petrel to basically, in Paradise, in order to be able to identify the critical contribution of the various attributes. So you can see a list of attributes right there, from instantaneous frequency to envelope slopes to bandwidth, sweetness, all the things that you're familiar with. We put all of those volumes generated in Paradise into the PCA analysis, and that was basically used in order to initialize and generate these self-organizing maps. So those 8 volumes that I listed in the previous slide are shown on the left. That was the input in order to generate these self-organizing maps. So then the next new workflow, the technology that just came out, uses the petrophysical data, right, in order to be able to set up a cross-section view, which is then capable of being linked directly to the data extracted along the wells for both the regular seismic as well as for the self-organized maps, right? And with a setup like that, the workflow continues. The self-organized maps are then integrated with the well log data and the lithofacies, and then the lithofacies are assigned to the self-organized map neurons. And here's where the magic happens. So what I use is I use an initial 3 facies in my initial test, right? In order to be able to get an understanding of the lateral distribution and the identification within the seismic of the various phases. I use different types of carbonates, high porosity, medium porosity, and a tight carbonate for the Midland farms. And almost immediately, I was able to generate 3-dimensional geobodies, right? In just a matter of minutes, that very much looked like the type of geobodies that previously it would take me many weeks, and prior to that, months to generate. So I was intrigued. So of course, with 3 facies, I decided, let's go and generate 5 facies. So here's the setup again for the actual seismic data, as well as the lithofacies and the SOM extracted data along the well bores, right? Then you set up this beautiful interface that is part of the lithofacies prediction, which shows you a histogram, as well as the multiple cluster-based analysis of the various facies, breakdowns, and distributions. Fully interactive. You can click on any one of these different neurons or clusters, look at the overall distribution, look at the probabilities in order to get a feeling for how precise and accurate the prediction is taking place, right? And then distributing that data and doing the mapping, the intersection effectively of the lithofacies with the neurons gives us the ability to create 3-dimensional geobodies. And again, especially with the 5 facies, the lithofacies predictions start to look very much like my previous work. Okay. There's a larger picture of that. And of course, the difference is that the work I previously did took me 3 weeks. With Paradise, I did it in under 12 hours. Well, actually, it was 13 hours, but I took a lunch break. So, lots of caveats, right? What's the caveat? Well, number 1, you have to be heavily caffeinated to do this for 12 hours straight, right? My wife was sitting in my office, making sure I stayed fed, right? Ran through the whole 12 hours. After about 10 o'clock at night, she asked me, "What are you doing?" Right? And I was like, "Oh, I'm close. I'm close." And she had no idea what I was talking about. So, but the other thing is software. You know, you have to be willing and able to take on new software. And you think like, yeah, no big deal. We all do that, right? No, we don't. Absolutely no, we don't. You know, there's many people, both in the industry as well as in academia, that have significant resistance to taking on new software, right? That's something we have to overcome. Even I have that from time to time. I have my favorite software. I have software that is difficult to use. One thing I can tell you about the Paradise software, it was an absolute joy to use. It took away all of the barriers to entry to software. It was logical, it was sensible, it was easy to use, and it produces results, most important. So, picture on the left, 3 weeks, picture on the right, 12 hours. I'm sold. So then I started doing a little bit more work, especially with Charlie Cairns' facies distributions, and created additional self-organized maps as well as these predicted lithofacies distributions. And if you just take a look at the overall continuity and connectivity of the upper picture, which shows the acoustic impedance inversion, and then at the bottom picture, it became very, very intriguing. And I just did this in the last couple of days, so I didn't really work out too many of these slides. But the overall continuity and connectivity that is predicted by the paradise lithofacies distribution is going to play a very important role in future conditioning of geostatistical distributions of porosity and permeability. Very important in this particular field, where, of course, we're tracking overall conformance of water floods, CO2 floods, as well as the carbon capture and storage. And that's a picture right there at the top of the actual geostatistical distribution conditions to the acoustic impedance production products, which show that in the future, what this picture tells right here is that combining the new results off of Charlie Cairns' facies model with the self-organized maps and the lithofacies prediction, in my mind, can lead to even more accurate subsurface distributions of these 3D lithofacies architectures. So, from my perspective, big success. Not just for the time savings, but more importantly, because of the value and the quality of the results. So, great way for people who are not experts at machine learning, and I definitely counted myself among that. If I didn't have, Dr. Frank Mail to call up at the Penn State, I'd be stuck. Yang Kang Chen sitting over there, he's one of our experts in machine learning. Of course, Sergey Fomel's group is doing fantastic work on fault extraction. Xinming Wu, of course, is famous for his FaultSec 3D. We've got Chao Li working on new stuff. Stay tuned for some papers specifically on that subject here in the next couple of months. Lots and lots of experts around the Bureau that know about machine learning. Zoltan Sylvester is another name. So nonetheless, I, with a degree in petroleum engineering as well as geology, was still pretty intimidated by this new technology. One of the ways in which I learn about machine learning, apart from talking to experts, is to run software that does machine learning yourself. Play with the parameters, change the inputs, do the sensitivity analysis, come up with multiple scenarios, and see if it can actually be validated by pre-existing independent data. And that's what we did with the lithofacies prediction. So then we have a similar type of problems with faults, right? Because we need to build three-dimensional fault models for the entire Permian Basin. This is important for both our petrophysical distributions as well as for the work we're doing for TextNet, where we're generating a three-dimensional velocity model for the entire Permian Basin used for seismicity research as well as time depth conversions. So fault extraction from 3D seismic. Well, great. Everybody here in the room, basically, who knows about seismic interpretation says, haha, I don't need a machine learning piece of software because I got one stuck right between my ears that does the best fault interpretation on the planet. So I don't need it, right? And I could not possibly disagree with them less. I mean, they're right. Our brains are so good at pattern recognition that the entire machine learning industry and deep learning is catching up. But they're catching up pretty fast. But there's a very important thing that machine learning and deep learning can address that we as independent interpreters have a bit of a challenge with. If you give the same three-dimensional seismic to two interpreting geophysicists, geologists, or structural interpreters, right? You're probably going to end up with three different interpretations of the fault, right? So how can we all agree that there is a baseline, something that we can all agree on that we can work off of? That's what I see the real value of machine learning fault extraction from 3D seismic. We need to be able to run something that can be parameterized, run over and over again, and that we can replicate, which of course is a lot more difficult to do when you are a freewheeling, free-thinking geoscience interpreter, right? Which is a good thing, by the way. So we have very complex faulting situation. You're looking at a bird's eye view of the Southern Delaware Basin. You see, horizontal wells in the Wolf Camp combined with 3D fault models, with seismicity data. And of course, here in this environment, we built these three-dimensional models, and then we start to distribute the actual velocities. So I think if I click one more, what happens? Yeah, the cross-section shows up. So you can see the faults in the basements right there, the velocity data in the well logs, as well as data that was donated to us by our friends at ExxonMobil, right? Some of the challenges with the velocity distribution or any sort of petrophysical distribution in the Permian Basin relates to the fact that you don't incorporate faults. Take a look at, see if my, if I dare to turn on one of these laser pointer, right there. That's what happens if you distribute based upon a high resolution layering framework for the Permian Basin, the actual porosities through the various zones from basement all the way to surface. You get leakage across the faults, right? Those black lines are basically just there for display right now. They are not constraining the actual geostatistically controlled distribution of these velocities. But if you do build a fully sealed faulted framework for an entire model for the Permian Basin, you can end up with these pictures. You can carefully constrain the distribution of the velocities or any other petrophysical data. So what that tells you is that faults are important. And here's I just put this little picture in there. I have to show that to Bob Hardish one of these days because he modeled the Waha field many years ago. And those beautiful over thrust structures over there is what we can incorporate in our structural fault framework model. So we thank TGS for the donation of their West Lindsey 3D seismic amplitude, and we're going to use that to kind of highlight what it looks like if you run Paradise and do the fault extraction. And that goes very fast. It approximately takes about half an hour to an hour per gigabyte of processing time. And if you have such wonderful machines as were donated to me by Alexander Cervedes, the PI of TextNet, and Xavier Janssen, who is the PI of RCRL. As a matter of fact, I think I first got that machine from Bill Ambrose when he was running STAR, so I have to thank him too. 32 CPUs, 256 gigs of RAM. I can run 4 Petrel projects all at the same time. And I can use all those CPUs, that's 64 computing threads, in order to blast through these volumes and do the fault extraction in a matter of minutes or hours, right? And these are the results that you get. So then I overlay them with the seismic, and I switch a cross section. This is one that comes off of the basement. So now we're looking to the west. You've got the West Texas Geological Society cross section, just for reference, from north to south, running through Pecos County. The surface right there is the basement. I've got 2 surfaces highlighted, the Woodford and the Ellenberger, and overlaid some of the results from the Paradise fault extraction, right, coming off of the basement. And what we're looking for is basement rooted faults, the ones that we're all so concerned about that could be related to triggering the lower and higher end seismicity that we see from saltwater disposal in the Permian Basin, right? Easy to interpret, difficult to reach interpretation agreement on between multiple groups, right? So that's why we're doing this work, right? So what we're doing is we're basically running Paradise, generating these fault patches, right? Once we have these fault patches, we then look at their individual properties. If you squint to the upper left-hand corner, that's a surface area. You can get dip, azimuth. You can also get patch confidence, which is a product from the Paradise machine learning post-processing analysis. And we can very quickly see where the big faults are. In the previous picture, you saw, of course, the one that had the big area. That was easy, but it also is one that has high confidence. So then, once we filter it down to the high confidence faults, this is what we see as far as the basement rooted faults in this particular section of the field. And of course, I took a little model that's a subset of the TGS West Lindsey dataset. And then I show some faults that were previously interpreted in the West Lindsey volume that were rooted in the basement. Okay? And that's what they look like. And that's what they look like if you just project them onto the cross section, right? And you can see how that relates to the overall background faults. And then you compare the two. And this is interesting. I was able to do the proper filtering. And that's, of course, that's the dial you have to turn. Those are the buttons that you have to click. Those have the widgets that you have to fiddle with in order to get this comparison. But those are all very reasonable cutoffs and changes. It was very easy for me to very quickly see a general agreement between the prior manual interpreted faults as well as the machine learning Paradise generated 3-dimensional fault interpretation. And then, of course, what we do is we take these faults and we incorporate them into a 3-dimensional sealed stratigraphic framework for this part of the Southern Delaware Basin. And those are the faults that we have right there. So we can easily incorporate this. And oh, by the way, what you see right here is, what was it? Probably one of the nicest compliments I've gotten was from Buddy Price, the great stratigrapher and Charlie Cairns students over at Devon, who called me a trail monkey. So proud of it after using the software for 30 years, right? But that's the reason why you see so many Patrol pictures. That's my integration platform. What I can tell you is that the Paradise has all of these tools already built in. So most of the work can actually be done in there. I'm just learning, right, to integrate all this type of stuff. But these fault models that you see right here can be used to generate a three-dimensional sealed faulted framework for this part of the West Texas, the West Lindsey the seismic volume. So those are the faults derived from Paradise. And then we start stepping up. This is the Devonian. You saw the Ellenberger earlier. And then we layer on the Woodford and we take it up to the Atoka. Right? So it's very easy, and that's the point I was trying to make, to have tools like Paradise integrated with your interpretation environment. Now, why is that so important? Well, because most of us spend way too much time importing and exporting data. It can take up to 60% of certain projects in data management. Complete waste of time, takes everything away from doing research and being creative, right? Okay, that's what I love about Paradise's approach. They have a direct Petrel plugin. I pull data directly out of Paradise and put it right back in. So you can pick any three-dimensional interpretation environment you're comfortable with, landmark, what used to be called paradigm, you name it. It's very easy in order to link the tools, but most importantly for Paradise, it's this Petrel link, which is fantastic, where I can move data back and forth. So then, once we have these faults confirmed, and we have agreement between the original interpreters for this field as well as the Paradise-derived fault, we then have to look at our overall regional geology and our regional tectonic and structural framework. So what we see right here, we bring in other seismic, we look at our general, mostly well-log derived fault interpretations and start to integrate those with the work that comes out of our Paradise models. So, and that so far has been very encouraging. So, especially for three-dimensional seismic volumes where we have additional faults, the comparison between the Paradise as well as the manual faults is going very well. One of the things that I'm seeing actually is how Paradise, and this is extremely powerful, is capable of identify faults in areas where previously we had not interpreted a fault, right? And that's when we go back to that area and we basically go and reinvestigate and add faults to a three-dimensional faulted framework. So just a quick shout out for why we built sealed fault framework construction is because ultimately we want to, we're talking about statistics, we're talking about geostatistics, we're talking about the value. This is more of a Michael Perch level comment here, but the actual spatial connectivity between cells and three-dimensional volumes as it relates to our geostatistical algorithms are very much benefit from being in its original depositional environment. So being able to take a structural model with faults and reconstruct it back to the original depositional level and then do our attribute distributions completely changes the actual distribution of these parameters from the pre-tectonic phases. So that's another advantage of modern three-dimensional software having this capability. So then, of course, we need to validate all this stuff, right? Validation is critical. In TechSnap, we're lucky because we have seismicity data, and I'd like to refer you to Yang-Kang Chen's recent publications where he uses machine learning to draw even more knowledge and information from this massive amount of data that TechSnap collects on its brand new 300 plus station network throughout Texas, right? And he uses machine learning in order to find even more detailed seismic events in the subsurface, which relate to induced seismicity, which in turn relate to faults. So we bring that data together with the results from our Paradise fault extraction in order to corroborate, compare, and in many cases validate either the interpreted faults or the seismicity locations. Great, that brings me to a couple of final slides, future work. You can imagine, if it's that easy to use, right, then I'll be encouraged to go and use it on every single seismic volume that we have, right, as well as all of the petrophysical data. So these are all the seismic volumes we have in the Permian Basin. Then I applied a little filter. We have access to about 75,000 well logs in the Permian. About 30,000 of those are good quality triple combo log curves. And I displayed those on top of all of the seismic volume I have access to for both RCRL and TextNet. So we got a pretty decent coverage, right? And if we drop down to lower quality triple combos, then we can lift that up from 30,000 wells all the way up to 75,000 wells. So we have hope that we'll be able to get good coverage for all of these seismic volumes throughout the Permian Basin in order to build this very important relationship in paradise lithofacies prediction between the petrophysical well logs and the 3D seismic in order to be able to come up with 3D seismic size, high resolution lithofacies model. So processing this petrophysical work takes a lot of effort. Here in the summer, we've made a big leap forward. The young man in the lower right-hand corner was my summer intern who used a combination of interactive petrophysics, TechLog, and other software to be able to process 7,000 wells petrophysically throughout the Permian Basin. So that took him one summer. Why? Because of software and computer advances, basically, right? And having a three-dimensional model really helps in the validation of this petrophysics and the tuning and the actual evaluation. Now he is an intern who just won the third prize at Monday's Houston Geological Society student job fair, right? Based upon a 5-slide presentation where he went up against mostly graduating upperclassmen, graduate students, and PhD students, but he got the third prize, even though he's just a freshman petrophysicist in college. The democratization of science. He was able to make this cross-section from shelf, the slope, the basin, showing the actual petrophysical distribution. And this, of course, becomes very important for both our future paradise work, as well as all of the other work that we use this for reservoir characterization, regional geological interpretation, linking everything back to Charlie Cairns's core and outcrop interpretation. That's where the petrophysics is going to play an important role. And then, of course, the models, we take them beyond the actual seismicity work and go into actual production data analysis. This is where I work with the likes of Frank Mail up at Penn State University, integrating all of the decline curve analysis, production forecasting data on each of the individual layers. And you see horizontal wells right here with, water EUR, estimated ultimate recoveries, your water cuts, and so on and so forth. So we bring all of this stuff into our massive laboratory, which combines well logs, seismic data, production data, and so on and so forth. And here's where the Paradise software is going to play a very important role. So we have a press release most recently at the AAPG, which was spearheaded by Hal Green. And Hal Green, picture lower right-hand corner, this donation would not have happened without his help. He's sitting right over there. So if you have any questions, Hal, thanks for coming today. If you have any questions about the exciting story from Geophysical Insights and the Paradise software, he can tell you some wonderful stories about how it all came to bear and some of the quality people and companies that they have worked with in order to bring this technology to fruition. So, of course, at the very top, we got Tom Smith, CEO of Geophysical Insights and a leading expert on machine learning. Most of you have been in this industry as long as I've been, which was since 1989 when I started at the Bureau running 3D modeling, right? Know, of course, Tom Smith from being the inventor of the world-class Kingdom software, which was a major success and is now owned by our friends at IHS/S&P and also available at the Bureau of Economic Geology. Actually, matter of fact, that group is run by my dear friend, Hank Chambers. So that's one of Tom's great accomplishments in this industry, to really bring easy-to-use software to the masses. Our very own Michael Young is quoted in this press release as well, talking about the value of machine learning and being very willing to talk about plans to collaborate and cooperate more between the university and Geophysical Insights in the areas of machine learning. All I can tell you is that the user interface is great. The help support options are fantastic, you know, and here's where I need to say this because very often we deploy software, but our students and our researchers don't necessarily have access to those wonderful resources that the paying customers get, right? They get blocked, right? Not so with Geophysical Insights. They opened up their entire support website. There's the total number of webinars, videos, instruction, theory, background has been wonderful in furthering my understanding of these sorts of machine and deep learning algorithms and techniques. So I strongly recommend visiting that website for a wide range of reasons. These are all the consortia that we have at the Bureau of Economic Geology. We've got currently, since I work both in Reservoir Characterization Research Laboratory, as well as for TextNet, that's the two places where we have deployed the software the most. But training, of course, is being planned for any group that is interested. So in conclusion, well, you saw it, right? I went from 3 weeks to 12 hours. So that convinced me to continue work with Paradise for both 3D lithofacies distribution prediction, as well as for fault extraction. And we're going to continue it on all of our 37 3D seismic surveys and integrate all of our petrophysical data moving forward. So stay tuned for more updates on that, as well as the publications. Great. Just want to thank all of the companies and groups that donated data. This is the list, and it's a wide range because without data, we can't do anything, right? So, and of course, especially from the RCRL group, we have these industry sponsors who collaborate with us very much down to the level of providing data, knowledge, insight into individual field level oil and gas reservoirs for CCUS, as well as for reservoir characterization, but also for a wide range of regional studies. And I look forward to working with them on implementing additional machine and deep learning methods and techniques. So thank you very much for your attention and for attending this talk.